For this video, we'll be covering how to do a fluid simulation using Acusolve and Virtual Wind Tunnel, and solving the simulation using high-power computing. The first step is to generate the geometry. You can use any CAD software for this. In this case, we're using NX 8.5. Now, for this example, we'll go ahead and do a simple simulation of flow over the sphere. So we go ahead and generate a sphere. Now, once you have your geometry, we can go ahead and export that to IGES format. For that, we go File, Export, IGES, and we go ahead and save this to any desired folder. In this case, we'll go ahead and save it to an example folder. We'll go ahead and label it as sphere. Clicking OK, we'll go ahead and export that. Now, once the geometry is exported, we can go ahead and open that with HyperMesh. Once we open HyperMesh, we do get this window that shows us many different options for different applications. In this case, we can use either the default or the Nastran options. So we'll go ahead and use the Nastran options. Click OK. Now we'll go ahead and import the geometry. For that, we can go ahead and click on the green arrow on the top left and go ahead and select Import Geometry. Now, in order to import this, we go ahead and click on the folder, and we go to the folder we created where we have everything saved, which is the example folder. Go ahead and import our IGES file. Click OK. Now, if you look down here, you do see an option that says Import Options. We click the arrows here, and it'll bring down this menu. Now, this is an important step since you do have to keep in mind that Virtual Wind Tunnel and Acusolve read everything in meters. So since the geometry was generated using inches, we need to go ahead and convert that by using the scaling factor. So by using this value here, we convert from inches to meters. Once you have set that value, you can go ahead and click Import. Once you import your geometry, you will see a line here, but in order to see the actual shape, you do have to click Shape Geometry. And that will go ahead and shape the geometry here. If the view is too close, we can go ahead and click Fit Model on the top corner here. And we'll have our geometry in the center. Now the first step is to go ahead and make the mesh, the surface mesh, for our geometry. In order to do that, we can go ahead and click on 2D, Auto Mesh, and that'll give us the options to generate a surface mesh. So first, we need to select the geometry that we wish to mesh. In this case, we can click on Surface here and click on Displayed Surface. This will select all of the displayed surfaces. In some cases, you might want to specify specific surfaces and not all of the ones displayed, but since our geometry is very simple, we can just go ahead and select all displayed surfaces. Once we have selected the surface that we want to mesh, we need to specify triangular elements, since Virtual Wind Tunnel and Acusolve only read triangular elements. Now, the element size, we can just go ahead and specify a value. In this case, we'll do 0.001. And notice how sometimes the software will go ahead and automatically change this value. A lot of the time what will happen is that the software will just exceed a certain tolerance, which means that it'll select the closest value to the value it chose. But this value is usually good enough to have a decent enough surface mesh, or you can go ahead and refine it afterwards. So we'll go ahead and just select mesh, and that should generate our mesh. Now that the surface mesh is generated, we can go ahead and check all of the elements. So to do that, we have to click Return. And one important thing to keep note of is by going to the Models tab here, we can double check that the mesh is actually related to the component card by clicking the Mesh button here. Now, if for whatever reason the mesh is generated on a separate card and a third card appears down here, then what you need to do is you need to make sure that the option here is selected, Elements to Surface Come. Once this option is selected, it will make sure that the mesh is generated to that specific card. Now, if we go ahead and click Return, we can go ahead and check the actual mesh. one important thing to check is duplicate elements or things like Jacobians, and we can go ahead and do that by checking duplicates, and in this case we can see that there is no duplicates found. In some cases you will find duplicate elements, especially with more complicated geometry, in which case you might need to delete those elements in order for the mesh to function properly. Now, another very important thing to check is the edges. This is something that affects more the connectivity between different meshes when you have multiple components. So in some cases you'll have some meshes that have interfaces between the two different meshes, in which case you might need to do an equivalence. In order to do this, we need to first find the edges. In this case, we don't have any edges, as you can see at the bottom left, which means that we don't need to delete or remove any edges. Now, in some cases, you will find this, in which case you might also need to do an equivalence as well in order to have a good interface between the two different meshes between different components. This will make sure that the model is completely watertight and make sure that there's no weird simulations or simulation errors happening later on, just because maybe there might be some fluid flowing between surfaces and stuff like that. So in this case, checking that is very important. Now that the mesh is generated, we can go ahead and export that to Virtual Wind Tunnel. In order to do that, we go ahead and click on the red arrow on the top left and select Solver Deck, Export Solver Deck. Now the options that we want to have for this are CFD, solver type Nastran Fluent, and then we specify a file name. Now we are going to save all of the different files onto that same folder, the example folder. In this case, we'll go ahead and call this sphere mesh. Click save. Once this mesh is exported, we can go ahead and open that with Virtual Wind Tunnel. Now that we have Virtual Wind Tunnel open, we can go ahead and import our geometry. Now, some important things to make sure that you have set up properly on Virtual Wind Tunnel are two main things. If you go to File, Options, make sure you have specified the location where Acusolve is installed. So just go ahead and click the folder here and specify exactly where the software was installed. Another important thing you must specify is the run path. So this is where the files will be saved once the simulation begins, and also where all the files that you might need in case you export the files, you might need to access this specific folder. So make sure you have specified both of these before starting. Once you have specified that, we can go ahead and import the geometry. To import the geometry, we just go ahead and click File, Import, and we go to this example folder and go ahead and open that surface mesh that we generated. Now notice that the geometry is positioned automatically here. We can go ahead and move the geometry and position it where we want by clicking Translate or Rotate. So we can go ahead and click the geometry that we want. You select the geometry and then click Rotate, we can go ahead and move it. Now you can go ahead and just drag and drop if you'd like, or you can be more specific by just selecting a specific distance. In this case, we'll go ahead and do 4 meters, and then we'll go ahead and do 2 meters in the Y direction. So if we click the Z direction, we'll go ahead and just click 2 meters on that, and that'll move it in the Z direction. Now you can change the size of your tunnel by clicking Edit Tunnel. In this case, we'll go ahead and specify the height to 4. And that should position our shape in the middle. Now that you have the desired size, we can go ahead and specify other options. Now, in certain cases, you might need to have certain refinement to your mesh, in which case you might need to add refinement zones by clicking the box here, and that allows you to move and edit certain refinement zones. this case, in order to simplify the simulation, we won't be using any, so we'll go ahead and delete them. Now, one other important thing for this software is to specify the different components of the body. In some cases, you might need to specify things like wheels, things like radiators, or the body itself. So for this, we'll just go ahead and make sure that the shape is a body. Now that all of the parameters have been set for the simulation, we can go ahead and start focusing on the actual mesh itself. If we click on the play button here, we'll get all of the different options for the simulation itself. Now, it's important to make sure you specify a velocity here. And there's two ways of doing this. You can just specify it here, or you could click down on the actual arrow down here and specify it down there. We'll go ahead and run a steady state simulation, and we can set a number of iterations. That's fine. And if we click on the meshing options, we can go ahead and specify everything else. Now here we have the option to turn on or off the moving ground. It's usually best to do moving ground, and on and off the rotating wheels option as well. Now here we can go ahead and specify the far field element size. For this, we can go ahead and either use one of the different presets, or you can use a user-defined size. In which case, we'll just go ahead and do 0.1. The near body ground refinement allows you to go ahead and change different options of the mesh closer to the ground. Here we can decide what percentage of the actual height you want to be refined, or the actual size of the elements that you want. Now, the boundary layer options are the most important options. It's important to be able to set the specific boundary layer height and the number of layers desired. A lot of the time, the original number of layers might be too low, but you can go ahead and automatically generate different sizes. So if you click the lightning bolt here, it'll go ahead and calculate automatically the ideal sizes. For this example, we'll go ahead and leave them, but there is a certain way to find the ideal size of the first layer and the number of layers. Now here, once we have set all of the different parameters, we can go ahead and click Run or Export. If we click Run, the simulation will be run on the local machine. If we want to go ahead and export, then we can go ahead and click here. Now, since we are running the simulation on a high-power computing cluster, we do need to export different files. And as mentioned previously, the files will be exported to the specific folder in which you specify at the options settings. Now, if we go to that specific folder where the files get exported to, we can go ahead and see the files that get exported. Now, note that every time you export or you run any simulation, the file will, or the folder will actually get labeled by the time and date that you actually ran that simulation. So in this case, we go to the current one, and we'll be able to see these files. Now, these files will be the files that you'll go ahead and upload to the server itself. And from now, in order to upload these files over to the server, we need to go ahead and use a special program called an SFTP program. In this case, the program we're using is called WinSCP. So once you have set up all of the server protocols and settings in order for you to be able to log into the server, go ahead and just log in. Now, on a program like this, you normally see all of the files of the server on the right side and all of your local files on the left side. In this case, you need to go on the left side and go ahead and go into the specific folder where the files got exported to. Once you're there, you can go ahead and transfer these files over to the server. Now, it's important to understand how you're going to do this. So what's going to happen is, in order for these files to be turned into the actual simulation, you have to do pre-processing by generating the mesh. This will require the server to read a job script. Now a job script looks like this. These job scripts will tell the server exactly what to do with how many computing nodes you want, and it'll go ahead and run the specific commands that you specify. In this case, we're going to use two different job scripts. We're going to use a job script for pre-processing, and we'll go ahead and use a job script for solving. Now, in order to submit the commands to run these, we need to use another program called an SSH program. In this case, we'll be using PuTTY. Now, once you specify all of the server settings, you can go ahead and log in. Once you're logged in, you will be able to submit the commands for you to run the job scripts that you specify in order for you to be able to solve the simulation. Now, in order to run the simulation, you use these types of job scripts. Now, for the pre-processing job script, here's a quick breakdown. We have all of the required commands for the server, so every single job script will require these commands here, which will specify the name of the job, the output file in case there's an error, the number of nodes or computer racks did you want, the number of processors did you want to use, which queue you want to use, normally is just set to normal, and the amount of time that you would like to use the computing node for. Once you specify all of these parameters, then you can go ahead and specify your actual commands that you want to run. In this case, we're running a command that specifies the actual license path. Then we can go ahead and specify the actual command that we'd like to run. In this case, we specify the location of the actual command. Then we specify where we're going to be running this. In this case, we're going to be using a folder called sim1. And then we specify what the simulation is going to be called and the number of processing cores we're going to be using. Now what this script will do is it will call the server, and then it will go ahead and run the pre-processing command. Once it's done doing the pre-processing, it will go ahead and copy this job script, which is the solving job script, and it'll paste it onto this folder, the sim1 folder that we specify. Now, in the server, there are two main file locations. You have your home and your workspace. So in your home, you have very limited space. You have about 1 gig of space, which means that you are only keeping small files such as your job scripts or anything like that, output files, those kinds of things, and you'll save them on your home. In this case, you can see that it's home CMATA 101. Now, if we want to jump to the work folder, it would be almost exactly the same. We'll go ahead and click OK. And we'll be able to see our work folder now, right? Which is located on work, CMATA, Lone Star. Now, on our work directory, we keep all of the larger files. This has about 1 terabyte of space. So in here, we actually have the installation files, and we have our simulation files as well. So in the simulation folder that I have here is where you'll be able to make the folder called sim1. And this is where we'll go ahead and save everything. Now, I'll go ahead and delete this one just to make a new one. Okay, so we'll go ahead and make a new one. We'll go ahead and call it sim1. This is where everything will be saved. Now we double click the sim1 folder, and now we can drag and drop all of the files from our local server. So these files are the ones that are in our folder, and we'll go ahead and transfer them over to the server. Now once the files have been transferred, we can go ahead and begin the simulation work. So what we're going to do now is we need to go back to the home folder, and what we're going to do is we're going to run this job script, the one that will do all of the pre-processing for us. Now, in order to run this job script, you need to use putty. Now, the command to run it, you need to first make sure you're in the home directory. If you just signed in, you are automatically in the home directory. Now, what we need to do is we need to type sbatch space and then whatever the job script is called. In this case, it's called JavaScript text. If we go ahead and hit enter, we'll go ahead and see that our simulation has been submitted. And this will go ahead and specify if there's any issues with the simulation, or if the simulation did not, or the job, I should say, the job did not get submitted correctly. Now in this case, everything went smoothly. Now if you want to check the status of your simulation, you can use the command sq-u and your username, and you should be able to check the status. In this case, we could see that the simulation is currently running. Now, once the simulation is done running, we can go ahead and check that by running the same command again. Now, if the actual job disappears from this, then we know the job has been complete. Now, if we jump over to our work directory, simulations sim1, and we refresh the files here, we can see the progress.
I went ahead and fast forwarded to the point where the simulation has completed now. So again, a way to check to make sure that your simulation has been completed is by running the sq command again. So sq-u and your username, and that should give you a list of the jobs that are running. So in this case, we can see that there's no jobs running, which means that it has been completed now. So some things to look out for once your simulation is complete to make sure that everything has been pre-processed properly is these 4 folders that we have here. Make sure you always have these 4 folders. This just kind of shows that everything was done all the way through. A lot of the time what will happen is that if there's an error or something stops, these folders will not be generated. Maybe you have 1 or 2 of these folders, but not all of them. So that's one big indicator right off the bat to be able to see how many or how far along you are in the simulation, and as well to see that everything has been running smoothly. Now, the other 2 files that are really important in this case are the log file and the mesh sim file. So the mesh sim file is the file that's generated with the mesh generation. So in this case, we get to see pretty much just the steps as to getting to the actual mesh generation. Now, there's no real important information on this file. The only thing you can really get out of this is the number of elements and number of nodes. But sometimes if there's an error generating the mesh, you can see here to make sure that, you know, something, in case there's an error code or something, you can check it here. Now, once the mesh gets generated, then the pre-processing gets submitted. So if we look at the log file is actually one of the most important files. So this one will have all of the information you'll need for any type of situation. So in this case, it'll tell you pretty much the entire process that it has taken. So in this case, it starts showing how it starts preparing the simulation, the boundary conditions, the actual mesh. It just starts setting up the entire problem for you in this case. And this is a good place to check and double check to make sure that there's no errors. Now, if there is any errors, sometimes they get outputted to the actual file from the server. So if we look at the job script has a certain place where it puts an error file. Now, sometimes that's not very specific. The error files from the server may not tell you exactly what's wrong, but if you look at the log file will actually tell you any error codes or any specific things that might be going wrong. So this is a really important file to check to make sure that everything is okay. So in this case, everything has run smoothly. We have both the log file, the mesh file, our 4 folders, and we got the actual job script copied over. So everything is set up and ready to go for the solving now. Okay, now getting on with the actual solving process. So After the pre-processing code or the pre-processing job script tells it to do the specific commands, and then it tells it to copy over this job script that does the actual solving steps. Now this is what we'll be submitting. If we look at this closely here, we can see exactly what's going to be going on. So we have all of the required commands for any job script on here. The only difference now is that we're going to use, for this case, we're just going to use 2 nodes with 48 processing cores total. If you wanted to change that, if you needed more computing nodes, you would edit this file here. Now, after you do that, you just have your regular commands here, like the command to call the license server. And in this case, we're going to be running acurun in this directory here, the Acusim directory. Then we have just virtual wind tunnel analysis. This is just the name of the problem, and then the input file is virtual wind tunnel analysis.inp. And then here we specify the number of actual cores that we're going to be running. So we have 48 processing cores here at 24 threads per computing node, which means that we're going to be using 2 nodes total. Now, a very important command for this case is we need to make sure we specify solve. If you do dash do all, for example, it'll do all of the pre-processing and everything that we just did. It'll do it all over again. So it's very important to put do solve. If you end up taking this off and you omit this command altogether, it'll automatically assume that you're trying to do all, and it'll just go ahead and redo all of the work again. So we want to make sure we specify that we want to solve. Now, in this case, the slurm command is just specifying the particular type of whatever scheduler you might have on your server. So this might change from one server to another. For the TAC server, it uses this -slurm. For something like the UTEP server, it would use -lsf. So it's just depending on which scheduler you might have for your particular server. So that's the actual job script. So this is the actual solving script. Now, in order to submit this script, we actually have to go into this directory here. Okay, so it's really important to do that. Now, when you first open your window, you're normally in the home directory, so you need to go to the work directory. In order to do that, we just type in cdw, and that should put us into the actual work directory. Now, if we can go ahead and cd into this simulations folder and then into sim1 folder, and we'll go ahead and be in this exact folder here. So we can double check by typing in ls, and we can see all of the files here are the files on here. So everything is pretty much ready to go. So now from this specific location, we can go ahead and submit the job script that we want to run over here. So in order to do that, we use the same command, sbatch, and then whatever the name of the script is. In this case, it's job script solve.txt, and we go ahead and hit enter, and it'll go ahead and submit that job script onto the actual queue. So we can double check that by using the same command again, sq-u and your username, and that'll tell us what's going on. So in this case, it's pending. Now I'll go ahead and fast forward the video to where this solving has been completed. Okay, so the simulation is complete now. What ended up happening here is normally once the job script gets submitted, you'll end up getting a second log file here. Sometimes what will happen is you'll just end up getting overwriting the first log file and then just erasing everything that it has, and it'll just keep writing whatever it needs after that. But a lot of the time you'll just get a separate one for each attempt that you try. So in this case, we get a second log file on here. If we go ahead and open that, we can go ahead and see exactly what happened. So on here, if we start scrolling down, we can see the iterations. So depending on how many iterations or the size of the time step, you'll have a certain number of actual files or actual time steps on here. So you'll be able to just check on here, make sure that you have, a proper convergence tolerance and all of that. You can check that here. So in this case, if we scroll all the way down, we'll be able to see exactly what happened. So on here, this is how we know that everything's complete. If you get this end time step, then you know that everything has been completed. So this is what this box here looks like. If you get this box here with this information on there, you know that the actual simulation has been completed. Depending on the number of iterations, you might have convergence, you might not. So if you end up doing something like, I don't know, like 1,000 iterations and it ends up converging before that, then you'd be able to just go on here and then just see what time step you're in, and then if it stops there and it gives you the ending time step, then you know it converged at that point. So now we can start focusing on the actual post-processing. Okay, so now for the post-processing, you actually have a couple options. You can either try running the post-processing on the actual server itself, or you can download the files and go ahead and run the files and open the simulation on your local machine. Now, there's a couple things to consider. So, for example, I have a few simulations on here. Um, if we if you end up downloading these files onto the simulation that or onto the folder where you started everything, it might take a good amount of time. So depending on how big the simulation is, you might not be able to, or it might take too long to download, in which case you might want to do all the post-processing on the actual server. The only drawback with that is that if you do the post-processing on the server, you might run into lag, and the actual server won't be as responsive, so it might take you a little bit longer and might be a little more frustrating to do the post-processing on the server itself. So when possible, it's always best to download the files and onto your local machine, but on certain cases you might have to run a simulation that's way too large. So in order to do the post-processing, if you want to do post-processing using Acufield View, which is the one that comes packaged with Acusolve, you can just go ahead and open Acufield View and then open the actual log file that you just had. So the only thing is that in the case of having the log file open, you might take a while to actually load the files. So now if you wanted to actually export the information to do post-processing on something else, however, then you might need to open the which one is it? The ACS file here. So you might need to open that ACS file using Acuconsole, and then from Acuconsole, then you would actually be able to export into any other type of post-processing that you might need. So in this case, I can go ahead and download all of these files, but that might take some time, so I'll go ahead and open another similar simulation to this one. So if we go ahead and go into data input, and then we do Acusolve Direct Reader, we can go ahead and read grid data. So here we have different results, so we'll go ahead and do, I believe I have a few sphere files here, so I'll go ahead and do I'll do this sphere here. So if we go ahead and open the log file, whichever is completed, it'll go ahead and read all of the information for it. Okay, so it went ahead and loaded it now. We go ahead and click close. We can go ahead and change the view here to the negative y. So here we got our actual boundary, or the actual boundaries of the simulation on here. Mind you, this one's going to be a little bit different, but it's a similar simulation. So now if you wanted to see exactly what's going on, you would have to click on the coordinate plane here and then create a new coordinate plane. Now you can specify if you want it on the x direction, the y direction, or the z direction. In this case, we'll go ahead and do it on the y direction. So here we get to see the actual mesh at that specific point. The slider here will let us go ahead and move forward and back within that within this actual box here. So this will give you a better view. If we do the slider here, it'll just move it within that direction. If you wanted to do it in the x direction, you can move it in the x direction this way as well. So in this case, we're going to do it in the y, and we'll just go ahead and center it. So we'll do 0 there, and now it's centered. So we'll change the view again, click in here, negative y. Okay, so now this will give us the mesh. Now to see any real contours or anything like that, we need to change the coloring from generic to scalar, and that'll change it to the scalar form. So in this case, we can see, for example, the velocity contours. So if you wanted to change that to pressure, you can just click select here and change that to pressure right there, and that'll give you the pressure contours. Now if you wanted to have like a continuous contour and not any of the holes from the mesh, you can just go ahead and change that up here in display type from mesh to either constant or contours as well, but that's a little bit different. So constant will show you whatever you want to see on here. So we can go back to, for example, x velocity, and you'll be able to see everything on here. So that's pretty much the basics to this. If you wanted to add things like a legend or anything like that, then you can just go ahead and show legend on here, and these are all the parameters. The color map is a little important. You can do a local range, so it'll fill in the colors depending on the range that you have, or you can go ahead and do, if you do filled color contours, then it'll just try to do, you know, a certain number of values that you set down here. So if you increase this value here, it'll go up to a certain point, and then that's how many colors that you can have on here. If you do it local, the max and minimum value will be set to that point. And those are pretty much the basics. From here you can just go ahead and export the pictures, you can do plots, you can do whatever you might need to do, and you can go ahead and continue doing the actual post-processing locally. Now if you want to be able to see the actual shape on here, you can click on the boundaries here and then create, and then select exactly which geometry you want to create. So these are all the different walls, but I believe the figure here should be the actual shape. So this first part here is the shape. Now that's the actual mesh. Now again, you can change that to the scalar value, but you can actually just change it to a faceted, and it'll go ahead and show you the actual geometry. So those are some of the different things that you can do. This software takes a little bit of practice mostly, but then you can do all of the post-processing on here very easily.